Okay, so let's get started. So, few announcements. First thing is, okay, so the stats intern Bayesian office hours is actually going to start this week. So it's going to be Thursday or Friday. I will send an email after class today. When are the hours and where he's going to hold the office hours upstairs in the math launch. And also solutions to homework 1 will be posted later today. I will post both the PDF and the LaTeX files because we're just waiting for one more student, remote student who joined a little bit late only last week. So once I got the homework from that student, I will be able to post the solutions. And I will also post the homework 2 cover page soon, either today or tomorrow, depends on how fast, like how much material we can cover today. And also because of what happened last time, if you guys can just remind me, don't forget to record, that would be nice. I already did that today, but for the future, just in case, and I appreciate that. Also, because I'm going to Swarthmore, Haverford tomorrow for 2 days, and there are 2 remote students over there, so I think we will have a extra shorter lecture on Thursday afternoon at 4. And it's okay if you cannot zoom in real time, but just as usual, everything will be posted on YouTube. So again, I think it will be shorter than usual. I just want to cover certain things before you can start doing homework. And that depends on how much we can get through today. But most likely it's going to be at 4 tomorrow. And yesterday or Monday, I think I sent out an email with a link to a Google Doc where I typed in all of the meeting IDs. So if you go to that link, and you can find the meeting ID there for the Zoom meeting on Thursday, like tomorrow. So I will send a reminder email tomorrow as well. But for all of us, if you want to Zoom in real time, you just need to download the Zoom app on your laptop or even just on your phone or tablet, and just join by the join meeting, join the meeting by the meeting ID, and then you will just hear like just gonna zoom in real time. Okay, so I will send out more detail later. Okay, so these are the announcements, and before we start today, I want to quickly maybe just mention a few questions that was raised up earlier today, because I was holding online office hours with 4 other students. So we have 4 remote students for this class. So a few things that they asked that I would like to actually bring up as a whole class. So one thing is, so one of the questions is how you can identify kernels. So last time I mentioned about this term kernel, okay? And we never really like formally define it. So the thing is, I think that question is really asking, okay, because last time we learned about the situation where you're doing a beta binomial model and you practice recognizing what a beta distribution is. Okay, so let me just bring this is where we left last time, and we can actually use this one to explain the the question as well. So this is the beta binomial model, and let me just show you what we did last time. This one is it's a little slow. Yeah, this slide is telling you how you can actually derive it step by step, not ignoring the marginal density of the data, right? And once we do the integral, like the trick over here is trying to recognize, trying to use the fact that this is true for any beta distribution. So we use this fact to come up with this normalizing constant over here, and that helps us to recognize that in the end, what we have is a beta distribution, okay? However, for most of this class, you will see that we're gonna ignore the normalizing constant. We're gonna ignore py, because we assume that it's given. We just don't know what it is. It's a normalizing constant. So the process just becomes so much, I guess, easier and smoother, because we're just gonna start with the prior, everything gonna be proportional. So I don't even write out the constant, right? Remember, like the gamma function constant for the beta, I don't even need to care about it, because I just care about what are the terms related to theta. So here with beta AB, I know that the terms with theta is theta raised to power of a minus 1, 1 minus theta raised to b minus 1, okay? For the likelihood, that's y given theta, and I don't care about the truth function either, because that's just a constant. I only need to care about theta raised to power of y, and 1 minus theta raised to n minus y. And you notice that in the end, the posterior now is just proportional, and here proportional really meaning that I don't care about any other constants, and I come up to this. Okay, so I guess the question asked earlier in the online office hour is, okay, how am I supposed to know this is a beta, right? So the thing is, for what we're talking about right now, we're covering this beta distribution. In particular, we're covering this particular beta binomial model. So for now, you should know, and from now on as well, since we cover this, you should know that you can recognize this as the beta distribution. And in particular, in order to recognize what exactly the beta distribution is, you should know that. So that's why we write the terms like this, -1. So once you see this, you should know that this is the two hyperparameters for the beta distribution. Okay, so so this is because we're covering it and you're being introduced to this new distribution, and this is what you need to know. But just to give you like maybe like a bigger picture of how to recognize kernel in general. So in the office hours today, we talked about, okay, how about a normal? Okay, we all know about this density. If y, say, follows a normal distribution, the density is py equals to 1 over 2 pi sigma squared, right? And the exponent, -2 sigma squared, y minus mu squared. Okay? All right, so now let me ask you a question. Suppose at some point, we're gonna do some derivation, and then the model involves this normal density. What, like in whatever in the terms, maybe it's in the proportional, maybe it's in equal, whatever. If you, what kind of terms you see that can convince you that's a normal kernel? Let's just say kernel is some unique features of that distribution that as long as you see that is the case, you know that it's a normal. What do you think? Anyone? I just wrote down the normal density over there. So if later when we're actually gonna like deal with that situation later, but not right now. But since the question is asked, how can we identify kernels? Just want to bring this up right now, because I assume everybody has seen the normal density before. So how would you think, what terms you will see then that can convince you that it's a normal kernel? Anyone? So there are two hyperparameters for the normal, right? There is this mu and this sigma squared, right? So any terms related to that, as well as the data, of course, will be helping you to determine that is a normal distribution, right? So if you look at this whole term, what is the constant? What would be the thing that I can put into the proportional sign that I don't care? The square root of 2 pi, right? That's not related to y, not related to mu, not related to sigma squared. So if in the future, which we will see anyway, that if you are left with the term at some point, sorry about the writing over here. If you see something like this, okay, that tells you that it's a normal distribution, okay, because that's the kernel. Yes, right? Good question. What do you think? And everybody else got it? Got the question first? Okay, so like Serenity was asking whether this 1/2 can be considered as a constant. So I guess unfortunately not in this case because that's important for the kernel. Okay, you really need to have this form in order to have a normal distribution with mean mu and sigma square. Okay, so this is one example, and I just want to bring another example to you because we talked about this in the online office hours as well. So later, so realize that right now we're talking about beta binomial, and the general framework of the beta binomial is, the chapter name is one parameter model. Okay, so one parameter model is easy to deal with. So for the binomial case, binorm and theta, n is fixed, theta is the only parameter, so that's the one parameter model. Okay, we start with this because it's easier to do because you only need to make inference about one parameter. Okay? However, if you think about the normal case, is it one parameter model? Not anymore, right? Both mu and sigma square are unknown. So like if you try to make inference of these two at the same time, it's not a one parameter model anymore. So it will be a little bit more advanced, which we'll do later. But I can still make it into a one parameter model. For example, if I assume that I'm not making inference about the variance, I just want to make inference about mu, then this will be a one parameter model. Okay? So under this situation, how can I recognize the kernel? There are more things become constant now, right? If I assume that sigma square is known. So based on this density, what kind of things I can get rid of now in the proportional sign? Anyone? So in addition to what we have got written off earlier, also sigma square is given, right? But over here, we cannot, just like the here, we think this sigma square, we still have to keep it there because that's part of what the density is. So in the future, if after some derivation, you came to a term like this, then that's going to tell you that it is a normal kernel and mu is the only parameter over there. Okay? Yeah, so just want to give you some other examples. So yeah, we're gonna like study case one by one, but in general, that's how you're gonna recognize the kernel. Okay, we're gonna accumulate more knowledge about those. Yeah, Emma? Yes, so kernel, yeah, here we're trying to define it pretty loosely. So over here, say for the for the beta case, the random variable or like the parameter is theta, right? So in the density, anything related to the theta is the kernel. They all together is considered as a kernel. Okay, so yeah, so for beta will be these terms, and earlier for normal, that's pretty much all of the things with y over here, right? But of course, with y, you also need the mu and sigma over here in order to recognize that. That is true. Okay, anything else? Okay, if not, I think we can continue our lecture from this slides. Okay, so okay, here, earlier we talked about, okay, if you don't ignore the marginal density of py, I mean marginal density of the data, you can derive it. But now, because we have seen that is the case, we can actually only care about what the kernel is. So pretty much, you start with prior, only related to theta, combine with the data, and then you come up with these posterior, and then you recognize that this is a beta. Okay. All right. So for the rest of this lecture, I think there are just other things related to. Okay, so I wrote over here related to beta binomial model and just in general Bayesian inference that I want to get covered in this particular context. Okay. So first of all, let me just show you this. We know that the mean, okay, so beta distribution for beta AB, we know that the mean is A over A plus B, right? That's just probability, the first order moment expectation of the beta distribution. So now, with this knowledge, we can actually write the posterior mean, right? Because now we know that the posterior, the new A is Y plus A, the new B is M minus Y plus B. Okay? So in order to write the posterior mean, I need to have my new A and new B, new A plus new B. Okay, so this is what you're gonna have. Okay, so notice here that I further factor this ratio into sum of two terms, and in particular, it is a weighted average of the MLE. So remember, MLE is the frequentist analysis. That's just the sample ratio. Okay, the number of yeses or number of successes over the total number of trials, which is Y over N. So this is this term. Okay, and the prior mean, because we start with beta A, B, so this is the prior mean. Okay, and so there is some algebra involved in order to show why this is the case. But if you look at this particular term, I'm just writing like W1, W2. W1 stands for weight 1, and this is weight 2. Okay, so we're using weights. Weighted average, you probably heard the terms before. So it's not just taking the simple arithmetic mean, but you're weighting two components here, and in particular, the two components are the only components, so they sum up to 1. Okay? So if you think in this term, what does it mean? The posterior mean, it is a weighted average of the sample mean and the prior mean. Okay, and the weights are specifically defined in this way. So in the bottom, it's both M plus A plus B, right? And the contribution of the MLE, the sample mean, is kind of depending on the sample size, right? And then the contribution of the prior mean is depending on kind of like a prior size. If you think about A plus B is the number or like the amount of prior information that you have. Okay, so if you, break down this total term, you will notice that, yes, the posterior mean is a weighted average of the sample mean and the prior mean. And I guess if you try to recall, like maybe let me bring back that particular slide. This might take a little bit. Give me a second. I was trying to get the plot. Yeah, remember here? Yeah, so this is back with the uniform prior over there. And you notice that, okay, remember last time we were doing, okay, this is probably roughly the posterior mean. Okay, I mean, it's not exact because it's not symmetric, like it's not symmetric along the entire line, but roughly the posterior mean. And then the prior mean, obviously for uniform 0, 1 is 0.5, right? And then the Y over N, which is the MLE, I think last time was someone volunteered about 0.66. Sorry about that, 0.66. And then the posterior mean, I think eventually when we return it, I think that was about, so posterior mean, I think it's about, it's very close to the very close to the MLE. All right, so maybe this is not like the best example to show that actually the posterior mean is a weighted average of the sample mean and the prior mean. But overall, if you were doing a beta binomial model, this will be the relationship that you will see. So the posterior mean is always a weighted average of the sample mean and the prior mean, and depends how big of a weight that you put on the particular mu and, particular over here. How big is the weight that you're putting for sample mean and you're putting for the prior mean? Okay, all right, so before we move on, what do you think? So if I understand, so N is definitely the sample size, right? The larger the N, the more data that I'm getting in some sense, right? And A plus B, so A, both A and B, they're just hyperparameters for the beta distribution. And if you consider, say, in this case in particular, if we consider this, the sum of this, A and B, to be a prior sample size, let me just use the term for now and I will explain a little bit later. If you think of this as the prior sample size, and this is just the data sample size, right? What does this particular breakdown of the posterior mean tell us? Sample mean is fixed, right, from the data. Prior mean, as long as you fix A and B, it's A over A plus B. Okay? So I guess I'm trying to ask, okay, because AN and A and B, in particular, if we only get one data set or like one set of data, then N is fixed. But I can still play with A and B, right? Say if I believe the mean of this particular theta a priori, like before, like in the prior sense, it is 0.5, I can do, say, 5 over 5 plus 5, right? A is 5, B is 5. That can give me 0.5 as the mean, right? I can also do, for example, 10 over 10 plus 10, right? There's so many different ways that I can specify that prior. But what is the difference? What is the difference here? Say like this case, I have A equals to B equals to 5. Here, A equals to B equals to 10. So even though in the prior, roughly at least at the mean, it's giving me 0.5. But what is the effect over here? So here, if A equals to B equals to 5, the sum of AB is 10, right? Yeah, and here, sum of AB is 20, right? So what would be the effect of increasing, say, the sum of A plus B from 10 to 20, affecting the posterior mean based on the breakdown of the posterior mean that we can get? Eli?
Means that the prior is going to have more of an impact on the, it's going to increase the weight from the prior.
Yes, exactly, right? So look at, this is why I'm trying to talk about this weight here and the importance of breaking this down into a weighted average. Okay, so if you look at here, so first of all, this is fixed. And this, in our example, the toy example, like both equal to 5 and both equal to 10, A over A plus B is always 0.5. So the only change that the sum of A and B is making is on these two weights, right? And N is fixed because that's the only data that we have. Okay? So the larger the sum of the AB, the higher the impact from the prior that you're gonna have for the posterior. So you can see that, okay, that's why we're trying to define this A plus B as a prior sample size in some sense. Okay? Because if you have like a larger A plus B, for example, in this particular context, you're gonna have a higher impact from the prior on the posterior, and it's dragging more towards to the posterior, like the prior gonna have a larger impact. Make sense? Okay, so that's why we sometimes like to talk about this as a prior sample size. So that would be another way that, but of course in the end, so remember like earlier we looked at so many different, I guess over here, yeah, so many different beta distributions. There's so many different things that you want to take into account, because earlier what I was talking about is only A over A plus B. That's only affecting the mean, right? Yeah, but of course, depends on the values of A and B, you're gonna have different shapes telling you about what kind of prior you might want to use. So there are other factors as well, but just so you know, choosing prior is really hard, and it's probably like the art anyway. So it is, there are many things that we need to take into account. Okay. All right, so this is, I guess, that. Okay, so this is just about the mean. What about the variance? Okay. What do you think about the variance? So here, I just wrote down smaller than the prior variance. And for this particular example, maybe it's useful just to bring back this plot again. This is uniform 0, 1 again. Okay? So the variance of the uniform 0, 1 is pretty large, right? It's anything from 0 to 1, right? Yeah. And so that's the prior that we have. But once we combine with the data, we come up with this posterior. This is much more concentrated, right? Yeah, so at least on this example, as you can see, the uncertainty is greatly reduced when you're doing this Bayesian analysis in this particular context. And in general, I mean, later you will see that there are many other aspects we will talk about, especially once you're not just looking at this simple like beta binomial model. Later you're going to look at more advanced models out there. But there are we always care about, okay, because you start with the prior, and you, together with data, you come up with the posterior. For the posterior, you really want to make better guess or make better inference once you combine with the data, right? So for this case, okay, even if I start with a uniform prior, which is very vague, very uninformative, but the data is really telling me a lot about how I should make inference. So not only the mean is greatly shifted to the data, right? Remember the plot, as well as based on this particular combination. Because uniform 1, 1 is beta 1, 1. So A is 1, B is 1. It's really small, right? Comparing to what N is. Remember, N is 1, 0, 48. So obviously the weight is greatly just from the sample mean, which is like 0.66, right? So that's why we see such a small difference between the posterior mean and the sample mean, okay? But not only that, the posterior variance, at least in this particular example, greatly reduced as well. And that's a desired outcome in some sense, because now you have less uncertainty when you're making an inference about something, right? We want less uncertainty, in some sense more accurate in some way. And that will be just a demonstration using this particular example that how Bayesian inference is actually getting us, in some sense, definitely better inference, more accurate inference about the parameter of interest. Okay, yeah, so here, I mean, because beta binomial is really like easy and nice, so you can see like a nice breakdown in this way. Yeah, but once we get more complicated models, will be less easy to see. But as you can tell that if I have the ability to plot things, I can still tell a lot based on how prior and data are contributing to the posterior. Okay. But for the beta binomial, it's a nicely done weighted average of the sample mean and the sample and the prior mean, and also the posterior variance is greatly reduced. And you notice that here, I wasn't even trying to provide a breakdown of things. It would be much more complicated. Okay, but from the graph, you can see that the uncertainty is greatly reduced. All right, okay, so here, yeah, just keep in mind, don't worry about, so for beta binomial, don't worry about the normalizing constant of the marginal density of y. We can just use proportional, and then you can recognize what is the density. It's a beta, and in particular, what their parameters are. Okay, yeah, so this is just bring it back again off the plot. Okay, so a few other things before we move to the lab that I want to go through part of it at least. So I wrote down other basics of Bayesian data analysis. It's really like widely defined, but there are certain terms that I think is important to be mentioned early on, because later we're gonna see those terms many, many times. But in the easy beta binomial model, it's, I think it's straightforward to define what they are and then get you a feeling of what are the other aspects that we care about when we're doing Bayesian analysis in the simple setting. Okay, so first of all, I talked about this term before, but let me just formally define it. Conjugate prior distributions. So earlier when we talked about beta binomial, I already used the term conjugate. So conjugate prior distributions in Bayesian analysis is defined to be if you start a class of prior distribution. So theta is the unknown parameter, and we use this P represent the class of prior distribution. We define the class to be conjugate for a sampling model y given theta if you start with the class for the prior, you're going to end in the same class for the posterior. Okay, so yeah, this is like the definition. As you can see that what we have seen so far, if the data model, which we also use sampling model, we use these terms exchangeably, sampling model and data model. Let me write it over here, data model. So what we have seen so far is if the sampling model y given theta is a binomial distribution, then the class of beta prior distribution is conjugate, right? Because what we have seen so far, you start with beta AB, and then you combine with binomial y theta, right? And then you came to beta A plus Y and minus B plus Y minus, I guess, I forgot. Yeah, I forgot the detail, but I hope you know what I'm talking about. Maybe I got some terms wrong over there. But okay, so this is example, like just a demonstration. You start with prior in the beta distribution, AB, and you end with the beta, but with a different beta. Okay, pay attention that you won't come to the same beta or same distribution. It's just the same class of distribution. Okay, all right. So okay, so conjugate prior distributions. This is example. So this is the definition, and what we have seen so far, beta binomial is 1. And something that I would like to get to for tomorrow's when I go down to Haverford and Swarthmore is to show you a different useful and commonly used conjugate prior is gamma Poisson. Okay, so prior data, and then you go back to gamma as the posterior. Okay, so anybody has some memory about this Poisson distribution? What do we use it for? Sorry? Rate? Oh, rate? Yeah, okay. Yeah, so Poisson has only one parameter, which is lambda, okay? And lambda is the rate. And what Poisson is doing is to modeling count of occurrences of things. Okay, so the only parameter, I forgot the PDF at the moment, sorry, but the only parameter for Poisson is lambda. And if you are using a Poisson model as the data model, you're trying to model count of occurrences of things. Okay, so gamma is a conjugate prior distribution for the Poisson model. So here, if you have your only parameter lambda for the Poisson model to be a gamma distribution, notice that this lambda is the rate. You're going to arrive at a different gamma. Okay, let me write gamma 1 and gamma 2, because I don't want to get the detail, and I don't remember the detail either. So you're going to arrive at a different gamma distribution, but it's still a gamma distribution. So by definition, this is a conjugate example as well. Okay, so this is what we will try to do for tomorrow for the shorter lecture. And just another note, maybe some of you already noticed or already would have guessed. Remember for the normal case that I was talking about, if I have a sampling model to be a normal, say people's heights, for example, and let me just fix this to be known. Let me just show you that I know what the variance is. I just want to make inference about the mu, which is the mean, okay? What would you, maybe it's hard to guess, but there is also a class of conjugate prior for this sampling model. So it will actually be normal, and normal. Yeah, but notice all of these normals are talking, like the first and the last is talking about the mu, and the middle one is talking about the data. Okay, always make sure. I think this is like a very not subtle difference. I mean, but if it's just the first time you're seeing it, or the first couple of times you're seeing it, you will always get confused. I think just like last time, the great question asked by Katie and Eli was, okay, why I don't put like a binomial for theta, right? They look exactly the same, right? However, for that question, I hope everybody is clear about that now. For that question, if you think about n choose y, theta, and 1 minus theta, I should write this way. Okay, this is really, if you say this is a distribution for y, okay, not for theta. Okay, but when we're doing the beta earlier, remember, is 1 theta raised to a, say beta ab. 1 minus theta raised to, sorry, a minus 1 over here. And this, even just looking at the form, you know that this is actually a distribution about theta. Okay, so that's why later, say for combining this two, look at just one more time writing this, you will notice that it's going to be theta a plus y minus 1, 1 minus theta n minus y plus b minus 1. And if you do this, even though it look very much like a binomial, but what we're doing is trying to come up with the posterior for theta. Okay, so that's why when you see this, don't worry about binomial, it's a beta. Okay, and usually this is, I mean, even just in the form, like the way, the steps of the derivation will tell you what it is. Okay, so just bringing back to the normal situation over here. Pay attention that I start, so first of all, the variance is fixed. I already know what it is, or I assume that I know. I only want to make inference about the mean for a normal set of data. So if I have a normal sampling model, so here maybe I should write y given mu, because that's the parameter. And this normal is the prior, and the prior is on mu. Okay, this middle normal is the data, and it's on y. Okay, and lastly, this normal is on the posterior, and to write it formally, it's mu given y. Okay, so always make sure that you understand the distinctions. And I think, yeah, I think as we see more examples like this, confusion will get away. But I can see that like at the beginning, maybe it's a little bit tricky. Okay, all right. So okay, so these are just a few other examples of the conjugate prior distributions, and make sure that you understand the definition. All right, the other thing that we actually did already last time is trying to come up with a credible interval. Okay, so credible interval is just a it's the equivalence of the confidence interval in the Bayesian sense. However, the interpretation is totally different. Okay, so we won't go through again what a credible interval in the frequentist method, but here, because in the Bayesian analysis, parameter is random, data is fixed, and because we assume that theta is random, we're putting a prior, which is uncertain, right? It's random, it's a prior distribution, and then we go to a posterior that it is still about this theta. So if you're gonna summarize, say, finding the middle 95% of the posterior, say for theta, you can really just interpret it as, okay, I have 95% chance that my true probability, in this case, the true value of theta is between the lower cutting point and the upper cutting point. Okay, so now because you assume that the parameter is random, so you can just directly make probability statement about the parameter. While in the frequentist case, as you remember, when you're talking about 95% confidence interval, it's just very convoluted over there. Okay, but in the Bayesian approach, because that's how you start your inference, you can make probability statement about the probability that the true value of theta are going to fall between these two values. Okay, all right, so it's pretty straightforward to do in R. I think you have seen it last time. And say, for example, last time I think we're trying to summarize using the, because we know the posterior is a beta distribution. We can use Q beta, that gives you the quantile, and you fit in what is the parameters, hyperparameters nu A and nu B over here, and then you just tell R, okay, I want the cutoff point of the first 2.5%, the cutoff point of the last 2.5%, and then this function, this command, is going to give you directly a 95% credible interval for this theta. Okay, but of course, you notice that, so first of all, it might not be symmetric, okay, because we're just using the quantile function, right? This two might not be symmetric. And a lot of times, actually, people might not try to return the middle 95%. So here I wrote down, you can also compute one-sided quantile-based intervals. So sometimes I only care about the last 95%. Then what I do is Q beta. And I only need to return point, if it's the last 95, so 0.05, right? And then whatever follows. So think about this. When we're doing it, because we know the posterior distribution is beta, and we know what is mu A, what is the nu B, the two hyperparameters for this distribution, we can just do anything pretty much, right? If you use the Q beta function, you can return any kind of intervals that you want, but you need to specify what you're doing. So what we're doing over here in the example is I'm returning the middle 95%, right? And this is a demo of the last 95%. And you can do other things as well. But of course, there are certain like fixed rules that people like to follow. But I just want to mention this to you early on that because now I know exactly what the distribution is of the posterior. I can summarize in whatever way that I want. Okay. All right. So this is posterior intervals, most importantly credible intervals for Bayesian inference. And there is another interval that we actually use more often in the Bayesian paradigm is called the highest posterior density, HPD intervals. Okay. So this will work slightly different, and I will, take a look at the form. And notice that this is different from, so first of all, you can see that it's not just using the Q beta anymore, right? Like even just in R, the way that you get it is different. But let me explain to you what does this highest posterior density mean? And then intuitively you get it in R, I mean, you have packages to do that for you, okay? So from the name, you can probably guess what it's trying to get. It's getting you the highest posterior density, okay? So posterior is a distribution, right? We know that for now. Yeah, it's a beta distribution, for example. So instead of, say, if I really want to report like a range of values that theta is very likely to be, maybe I don't want to do the middle 95. Maybe I don't want to do the first 95. I don't want to do the last 95. I want to report a range of values that's most likely to be the most likely 95, okay? So instead of like using the Q beta function, try to return using the quantile-based methods, we are actually doing what we're, maybe this plot can show you roughly what it is. So we're trying to only cut off when we reach the most likely 95%, and we're gonna stop. So on this graph, yeah, this is actually hard to do, I guess, with the iPad, because usually I can just like show you how it looks like. So let me just try here. So generally, the ways to do it is, okay, this is a density, right? This is a density. Density, like this curve is the density of the posterior. So this is the most likely, right? Makes sense? It's the highest. And it's, I mean, because this is the posterior density, it's most likely. So if, imagine that you're gonna have a horizontal line, just move from the top, and you just keep moving downwards. You just keep doing, and you're computing how much is already included, okay? And you stop when you get 95%, okay? So this is the reasoning of a highest posterior density intervals. So you start from the top because that's the most likely, right? And I keep moving down. And I want to report the 95% most likely values for theta. So I just keep doing, because whatever above the line is more likely than whatever is below the line, right? Based on the density plot. Okay, so I will keep track. I move the line further down. I keep track until I reach 95% above the line, and I'm gonna stop. Make sense? Yeah, so this is the, I think the rationale for this HPD, and you can imagine it's actually very hard to compute if you do that. Yeah, Tony? Good question, I forgot. Okay, I will get back to you about that. So Tony's question is, what is 0.14 is? I guess I don't remember, and I will get back to you, yeah. But this is, again, written, it's in one of the written packages for to do it. So I think it, yeah, let me get back to you later, but yes, there's some other special syntax over here that you need to pay attention to. So yes, I will do that next time for sure. Make sense? Yeah, so I think in Bayesian methods, we like to report HPD more than just the quantile based, okay? Because now you're already putting a distribution on the parameter, and now the posterior, you come to a posterior, and then I want to report the most likely first 95%, but not something just in between. Okay, so this is the rationale, and we will see, yeah, so in labs and stuff, we'll see other ways of how you can get it. I mean, this code is one way to do it. I think there are other functions out there, but overall, this is the rationale, so you should make sure that you understand what it is. And that's why if you see this, that's what it means, okay? Given the data, anything above the line is more likely than anything below the line, okay? But just imagine this horizontal line keep going down, and you stop when you hit 95% above it. Okay, so this is, I just took a photo from the textbook. I think it's a really good way to show it. It's pretty much just doing what I was describing earlier, but they give you different examples of, okay, like you start with 50%, 75, 95, et cetera, and you see that depends on the shape of the density of the posterior. The HPD intervals most likely going to be different from the quantile based, right? Because quantile based is only getting in the middle 95, but the HPD interval is trying to go from the top until the end.
So if you have a distribution of more than one mode, does that mean that your HPD interval will be
Good point. So Eli's question is, let me show it to you. Okay, I should be able to draw it over here. Okay, Eli's question is, okay, what if we're gonna have a, let's just make it even more complicated. They're not at the same level. Okay, so if this is your posterior density, if you try to return the HPD interval using the same way as we were describing, then of course, you will try to start the line and then keep going, keep going. Maybe you need to keep going until here. Let me use a different color. Maybe you need to keep going until here to return your HPD interval, right? So what does that mean? This plus this add up to be 95%, right? But it's an interval about theta, like the unknown parameter. So if I report it, it's gonna be two intervals in some sense, right? And they're not overlapping, yeah. So I think, I actually don't know exactly like in practice what people do, but for me, I think if we try to follow, unless they have some other design rules out there, otherwise I think you're gonna return, like you're gonna report this two separately. And you probably would like to comment that, okay, it's a bimodal or multimodal distribution, that's why you're gonna see this. Okay, good question. Anything else? Okay, so yeah, so for the most simple or like easiest example, this would be roughly how things will look like, and then that's just gonna, you have this line and keep going down, okay? And the textbook example, I actually recommend you to go back to read it carefully. This is example that you're gonna have different quantile, like 95% quantile based, like the middle 95, that interval is different from the HPD, which is not surprising in a lot of cases. And I guess for the cases that Eli raised up, it will be even less surprising, right? So the shape of the density, the posterior density can be anything, I guess, yeah, depends, yeah, I guess. So in this case, you will, there will be very little resemblance between the two intervals that you can come up with, okay? All right, so there's this, and I think, yeah, one last point. So in Bayesian analysis, we are not only curious, I think maybe for some researchers more than the others, you're not just curious about, say, like making inference about this success probability of how many, the success probability of teenagers going to have a television in their room. You might want to make a prediction out of it, saying that now, based on what I have so far, I want to make a prediction for the next set of kids, predicting whether they're going to have a television at home or not, okay? So maybe not so much like interest in this problem, but like even just in any kind of stats problem, people like to make forecasts and predictions, especially I guess for like time series type of data. You might want to like predict the stock prices for the next few days or next few years, et cetera, et cetera. So in that context, I guess predictions make more sense. But even just here, I want to use, just follow this beta binomial example, because if you try to derive what the predictive distribution is, you can do it, okay, for the very simple case. So here, let's see, we use y tilde, and it's only for one person, okay, one extra outcome, because it's just for one person is binary, right? It's either no or yes, whether that person has or not. So let this y tilde is binary, be an additional outcome from the same population that has yet to be observed. Then the predictive distribution, which is the distribution of y tilde, is the conditional distribution of y tilde given all of the data you have seen. Okay, so let me slow down here a little bit, because this might be, yeah, definitely probably the first time you would see any kind of things like this. So first of all, notice that when we are talking about predictive distribution, the parameter is gone, right? Like at least in this form, right? You have this y tilde given all of the other data that you have, okay? So parameter is really just, I guess, there to facilitate how the analysis can be. And then when you're trying to make prediction, you're making like a prediction for a new, like an additional outcome, like especially like if the wording is additional outcome from the same population that has yet to be observed. So assumptions over here, very important, same population, okay? Because you are using, say, whatever you have about the theta that you make inference about, and that theta is only for that particular population that you're trying to deal with. Anyway, so over here, notice that theta is gone, okay? So what this is really telling us, so we define predictive distribution or any prediction is only based on the observed data, which makes sense, right? We want to make prediction based on what we have seen before. And theta is really just a data model out there. Theta is, say in this case, is a binomial, is the success probability for the binomial, okay? So we define predictive distribution in this. Even though we define this way, we're still gonna need the help of theta because we already have some inference about it, okay? So this, if you look at this line, nothing too new, right? It's conditioning on all of the data already. I know that the conditional distribution of y tilde, given everything, given all of the observed data, will be, if I have the joint of the prediction and the parameter, given all of the previous data, and I integrate out theta, right? So this is what we have seen before, like, I guess if you do P, A, given B, is the same as E, A, C, given B, and you integrate out C, something like that. Okay, so nothing new, but maybe like the first time that you've seen this before. And the reason why we want to use this is because, okay, now I have the joint of the prediction and the parameter given the data. And that is really just a product of two terms over here. This is the posterior, right? We have it already. We made inference about it already. And here is just making, I guess, the product work. So in this case, is the conditional distribution of the prediction given the parameter and the data. So one last thing over here, I think simplify things is, what is this? You notice that like from this step to next step, this whole term becomes a theta. And that is true because, what do you think?
Theta is our probability of success.
Thank you, yes. Yes, so theta here, because it's a binomial model, right? And in particular, because we're only making prediction for one, it's Bernoulli, right? And theta is the success probability, okay? So if I'm trying to predict that it's a success, it's a new success, then this would just become theta because that's the success probability. And this is asking for the success probability. Okay, so that's why this term becomes theta. And what is this? This is again probability review. Theta, integral of theta multiplied with this density, but it's a posterior density, right? So theta, so this is expectation of the posterior pretty much, right? Let me just write it again. Expectation of x, if x is fx, the expectation of x for a continuous variable is this, right? Yeah, this is what we're using to show why this is expectation. However, everything now is conditioning on the data, I mean on the observed data, so this becomes the posterior mean. And this is what we know, the posterior mean. Okay, from the previous binomial model. Okay, so maybe it's a little involved for the first time to see it, but this is, I just want to show you that predictions can be done and you can analytically do it anyway, right? But later in next chapter, we're gonna start talking about Monte Carlo approximation, and you'll see that over there, oh, instead of, I don't want to deal with all of this, this looks complicated. Why not? Because that, what is it? Y tilde equals to I given theta, and all of the data will just be the posterior distribution, right? Will be the posterior of theta given all of the data. Okay, yeah, because that is true, and I can draw log theta already because I know it is a beta distribution with a plus y, n minus y plus b, something like this, right? So if I know exactly what theta follows, then I can draw, I can use r beta, right? I can draw a new theta from r beta, and then that new draw, maybe let me write theta tilde over there to represent as a new draw. Then what does that mean? Once I have a new draw, which is the success probability, I just do a Bernoulli to get a new y. Okay? Yeah, maybe it's a little bit too fast. Let me just explain this one more time over here. So I was saying, okay, this all looks fine. It's very nicely done, but I don't want to deal with any of this. This looks complicated. So another way you're going to do later in next chapter when we're talking about Monte Carlo approximation is you can actually utilize what you have already inferenced about the posterior to draw new predictions. So the procedure works as this. What do we have so far? We have the posterior of y, okay, which is beta, a plus y, n minus y plus b. Okay, I guess I just realized maybe here it's slightly defined differently. So here you have like multiple y's. So I think this is more talking about, okay, I have multiple sets of samples. Okay, but so far earlier we're just looking at y, one copy of y, because we only have one sample, but this is more generic, talking about any kind of, you have more than one sample. Okay, but let's just use the one sample example to demonstrate how to do Monte Carlo approximation for prediction. Okay, so let me explain this again. So I have the posterior, and I know the distribution of it. I know it's a beta. So what I can do is, first of all, I draw a new, so anything with the tilde, we just use it to represent a new draw. So we do new theta as a beta draw. So here I'm using r beta. Okay, and the parameter is a plus y, n minus y plus b. Okay, so I draw a new success probability for this new additional observation that I haven't seen yet. Okay, so first step. Second step is, okay, because I know if I know the new success probability, it's gonna be a Bernoulli draw for the new observation, right? Because it's binary over here and it's only one. So what I can do is I can actually draw the new observation from a R Bernoulli. I think it's I forgot, maybe just then one theta tilde. and then I get a new prediction. Okay? Yeah, so really, so for simple cases over here, we can actually derive the prediction for beta binomial distribution to be this. But at the same time, later on, so we'll see more of this later, so don't worry, but I just want to plug this in early on, because once you have access to like statistical software, there are so many things can be done in addition to try to analyze things analytically. Okay, so analytically, this is what this will be, right? The probability of success. So I'm just going to do a Bernoulli draw. So R Bernoulli over here as well. Okay, but I can also do it in 2 steps. I draw a new random draw from the posterior, and then based on that number, I can come up with a new prediction. And I can do that for so many different observations if I want. Okay, so I think, yeah, prediction is pretty much, yeah, so in the end, you can also try to come up with the probability of failure, and that's because it's binary, so the probability will just be 1 minus whatever I have come up with earlier. Okay. Yeah, so I did do, I think, a predictive distribution for this particular example. That's pretty much just plug in all of the numbers that we have with the television example. Okay, so in the end, you see that the probability of having a new success is 693 over 10150. Okay, and then you can just make a Bernoulli draw, and that will be a new prediction in this particular context with the data that you have. Right, so in the end, yeah, you're doing, okay, so yeah, over here you can do binomial, but it's only 1 sample size, and then that will be, you can draw it from the Bernoulli, binomial, which is Bernoulli in this case. Okay, make sense? Yeah, so I think you just need to like maybe sit down, look at things a little bit more, couple of more times. It's, I think the derivation part is not hard, it's more about how to think about those problems. And prediction is very important for any kind of analysis what we want to do. So this is very important. And I did just put some slides. I don't want to go through them. It's just classical inference for data. That's how all of the, say, the MLD, and then also like the confidence intervals, et cetera, for estimating a proportion, which maybe some of you know, some of you don't know about it, whichever is fine. I just put a few slides over there as how you can do it, and that's just doing maximum likelihood estimator, and then getting all of the covariance, et cetera, for that. Okay, so if you're interested, feel free to read that part, but it's not required for our class, just FYI. And maybe you can see some matching or not matching between the 2 methods for the same thing. Okay, all right, cool. So we got about like 15 minutes more, and I did ask you to bring the laptop, so we should use it since we brought everything. But so open your laptop, and let me actually bring this on mine as well. So if you go to Moodle, you will see that I posted a PDF under this particular section. I call it Lab 1. So if you go there, oh, give me a second. Yeah, go to Moodle, Lab 1. There's a PDF document over there for you to get the lab material for today. It's not a long lab, but maybe we won't be able to finish it, but I will provide the solutions. I will provide the solutions after class. Sorry. Okay, so you'll be able to get it. Okay. I have to move this. Okay, so let me stop share over here and try to share this one. Okay. Okay, so please go to the lab and then find the particular. All right, So let me explain a little bit of what this, so it's actually from the textbook, but I just rewrite it. I mean, not rewrite it, just copy the questions, but I always select the first view. Okay, it's not showing. Okay, over here. Yes, got it. Yeah, so this is the problem. And this looking at something different from what we have seen before. It's still beta, okay? But instead of just putting one beta, so we know that like beta distribution, you can do, in R, you can do different things, but now we're trying to figure out, like looking at a situation, okay, just one beta might not be enough. So how about I may have a very special belief that it's not just one beta, it's two different types of beta, but I want to combine them in some way. Okay, so the formal term for this will be a mixture, okay, a mixture of two in this case. And we're trying, for this exercise, we're trying to explore a mixture of beta priors, and in particular, a mixture of two beta priors with different weights. So again, the idea of weights come in. So weights, W1, W2, if you have two components, the two weights should add up to 1. Because they add up to 1, and then depends on how you're going to play with the weights, because you might have stronger belief in one case and less strong in the other case. So here, part A and B are trying to ask you just to plot two separate betas. The first one is beta 2, 8. The second one is beta 8, 2. Okay? So two beta distribution, you see that A plus B both add up to 10. Okay? However, of course, A is smaller in this case, in the first case. So just looking at the mean, you know that it's A over A plus B. So the first beta are going to have a smaller mean than the other one. Okay, but yeah, so A and B are just to try to make you practice plotting the prior, the likelihood, which is the data, as well as the posterior as functions of theta, and also practice using like all of the different functions in R. Say like if you try to get the posterior mean, you will be able, and then mode, standard deviation, and also a 95%. So here I'm only asking for quantile-based credible interval. So not the HPD that we talked about before. You're just gonna use Q beta to do that. Okay, so A and B, B is just repeating A using a different beta. And C is what we were trying to cover, like mostly important over here, is now I'm looking at a mixture of beta 2.8 and beta 8.2. In particular, I have 0.75 probability for the first beta and 0.25 probability for the second beta. Okay, so now I still have one prior distribution, but it's a mixture of these two. Okay, and part C is asking you, so first of all, we need to figure out how I can come up with the prior distribution. I tell you 75% to be beta 1, 25% to be beta 2. Think creatively how you can do that in R. And then lastly, I asked you to plot this prior distribution and compare it to the two priors before and describe what sort of prior opinion this new mixture is trying to represent. Okay, so I don't know how much we can go through, probably not so much anyway, but let's focus on part A for today, and I will walk around. So I didn't provide like a sample R code for today because I think getting the plots, like the posterior, prior, and likelihood should be okay, especially with the prior and the posterior, because we know it's beta. So with the D beta function, you might be able to get it already. And so for A and B, that's mostly what it is. And C is a little bit more advanced, but should be all right. So let me just maybe like spend 2 minutes walking around to see how people can do it, like how much you can do. And if there's like just missing pieces here and there, I'm happy to maybe demo some codes to start with, so you know where to start. So beta 2.8. Okay. So very similarly done as before in the normal case and the logist case. We can start doing something. Yes, the question, yeah. So for the likelihood is y given theta, right? So yeah, please read the question before the ABC part. The question is saying that we're trying to estimate the probability recidivism based on the study in which there are 43 individuals in the study. And, oh, sorry, there's a typo. There shouldn't be a D over there. It's just Y equals to 15. So that's number of 6. So Y is 15, and it is 43. So, that's okay. We can just do I mean, I provided, like, I already prepared the solution, so I will just send it out after class. But with the remaining time, I still wish that you're willing to try a little bit before looking at solutions. It's some extensions of the problem of like question 4 that we have done from the homework. And after 2 more minutes, I will just demo how to do part A, and then I'll post the solutions so you can replicate that for B and go back and think about it. So maybe something to start with, because now we're trying to plot this as functions of theta, and theta is the success probability. So if you try to initialize a vector of theta, you should initialize it from 0 to 1. So remember, for the normal, like in the demo code, I did -20 to +20, but for theta now, it's from 0 to 1. So you can initialize a vector of whichever length that you want, but you should initialize it from 0 to 1, and you can make smaller increments as you wish. Okay, so okay, so that maybe I will just stop talking about what I have so far, and because we only have like 3 minutes left, I think I should be able to cover. Okay, can you see my QR code? Okay. Cool. I mean, yeah, I mean, if you want to try it by yourself, don't worry, I just keep talking a little bit over here. So I first initialize the data. Y is 15 and is 43. And second here, I make a sequence of possible values of theta. Again, I'm doing like very close to 0, very close to 1. I'm doing 1,000 of them. Okay. So different ways of doing it. Here, it's like this using SEQ, stands for sequence. And you can tell the starting value, the end value, and tell R how many values you want instead of giving the increments. But you can also get like, I forgot the term. Yeah, but like getting the increment over there. And down here, I also have one more line just to later, because I want to plot 2 graphs on 1 page. So I use this PAR, and then in the parentheses, mfro equals to C12. So like within there, 1 and 2, you can think of it just as a matrix. So it's just 1 row, 2 columns. Okay, I'm trying to bring 2 plots side by side. So first of all, I define, you can do whichever you want, but I actually write a function for the binomial likelihood. It's nothing fancy. So you write a function, and the only input that you have is theta. And in the function, I'm just writing what the binomial likelihood is. Okay. Choose function, choose n, like n choose y, multiplies with theta raised to the power of y, and 1 minus theta raised to the power of n minus y. Okay, and I write it in a function because later I can just run it and then get the density. Okay, so if you do that, you will see that, okay, I can actually first of all plot the likelihood. Okay. Likelihood again is a function of theta. So on the x-axis is theta from 0 to 1. Okay. All right. So there's some, yeah, I mean, there's certain things I put in over here, say like I want to bring the Greek letters into my legend, or not legend, sorry, like the labels, etc. So those are ways I can do it. And the second step is how to get the prior and posterior. Okay, so the prior I know is beta 2, 8. And the posterior I know is beta A plus Y and B plus N minus Y. So I just let first initialize A and B to be 2 and 8. And down here, okay, so I plot the posterior first, okay? So let's look at this a little bit more carefully. Plotting the posterior first in the x-axis is the theta, right? In the y-axis is d beta, right? Evaluating the density of this beta. And for that density, I again fit in. So d beta, there are 3 inputs that you need to tell R. First one is the theta value. So that's the sequence or like the vector that you have. The second one is the first hyperparameter, a plus y. Second one is, the third one is the second hyperparameter, b plus n minus y. And I use both for the type. I use red. I use the first type of symbols over there. And I tell R what the label for y is, the label for x is, and I have the title, which is in main, the prior and posterior. So if I do that, you see that this is my posterior. Okay, my posterior in red, yeah. And the second line over here is just to do the lines. So that's plotting the prior on top of the plot that I have already. So same idea, you fit in theta, you use the d beta you use the d beta function, and I just choose a different color and a different symbol, but I guess there's just so many of them, so they look like the same. But yeah, okay. And the last one is the legend, and I just put on top, right? And then telling the red one is telling the reader, the red one is posterior, and the blue one is the prior. Okay, so yeah, so and then sorry, lastly, the last few 4 lines over here is trying to report the mean, the mode, the standard deviation, and the quantile. So you notice that for mean and mode and standard deviation, I'm trying to use formula. I'm not like generate random draws and then summarize. But you can also generate if you want. And the last one, I'm to because it's a 95% quantile based interval, so I use the Q beta function. Okay, so I will post this right after class, and then so part B is very similar, and part C is something very interesting. I actually encourage you to think about it before you see the solutions. But of course, I mean, yeah, feel free to ask me questions as long as you have any of those. And all right, okay. So more information later. I will send out info about the shorter lecture tomorrow. Feel free to zoom in if you have time. If you don't worry about it. I will post things online. Okay. Right. Let me just stop this really quick.